Thomas Kuhn is a highly respected scholar of the 20th century and author of The Structure of Scientific Revolutions. Kuhn describes a short history of the development of science in the Western world. Science is about identifying a phenomenon and using logic and reason to understand that phenomena. An online definition of science says, quote, "The intellectual and practical activity encompassing the systematic study of structure and behavior of the physical and natural world through observation and experiment." Science can also mean a systematically organized body of knowledge on a particular subject, for example, physics, life sciences, chemistry, and geology. The goal of science is to explain natural phenomena by finding patterns of behavior and using the pattern to make accurate predictions. Science begins with observation of a phenomena. Examples of phenomena that have fascinated scientists throughout the centuries: the pendulum, the nature of light, the structure of matter, disease and its causes, patterns of behavior of the sun, moon, and stars, and of course many others. When several theories on the same theme merge, they become a paradigm. According to the online definition, a phenomenon is a fact or situation that is observed to exist or happen, especially one whose cause or expectation is in question, and also an object or aspect known through the senses rather than by thought or intuition. The quest to understand the why and how of study of phenomena triggers research which sometimes leads to establishing scientific facts. A fact is an irrefutable truth. A scientific fact can be verified by observation and/or experiment over and over again, giving approximately the same result. For example, seawater contains several dissolved salts and minerals. Experiment: heat seawater until all the liquid evaporates. Result: crystalline residue of salts and minerals remain in the container. This experiment can be repeated again and again, producing the same result. But sometimes there are unexpected circumstances that do not fit, called anomalies. According to an online definition, an anomaly is something that deviates from what is standard, normal, or expected. A situation or event that arises cannot be explained within the framework of a given theory. Anomalies are inconvenient but important because they drive research either to confirm existing theories, discover new phenomenon, or abandon old theories to form new ones. A simple anecdote. A boy, Tom, grows up believing the theory his parents taught him, that all stones, when thrown into water, sink to the bottom. One day he is on the beach and finds a stone and throws it into the sea. To his amazement, it sinks and then floats to the top. He realizes the paradigm taught to him by his parents is shattered. He runs home and tells his parents. His father replies and says, "But that is what our parents and grandparents taught us. Sorry, son, we didn't know." The theory must now be changed to most stones, when thrown into water, sink to the bottom. The rock is pumice, found on some beaches, a light rock with a density less than water, full of tiny holes, left by escaping gases, which is thrown out of ancient active volcanoes. It floats because it is less dense than water. The point made here, simple as it sounds, is theories and paradigms have to change as new knowledge is gained. When a phenomenon is initially identified, ideas are brought together to form theories, and the theories are then tested by forming hypotheses, then making experiments to see if the theories are valid. This is the nuts and bolts of science. Theories fail because anomalies are found that do not fit the theory, so the theory is no longer viable and must change. Kuhn says that paradigms, quote, "are a framework containing the basic assumptions, ways of thinking, and methodology that are commonly accepted by members of a scientific community, a cognitive framework shared by members of any discipline or group." He uses the term paradigm in different senses. He calls accepted paradigms ruling paradigms, or grand narratives, worldviews, and related terms such as paradigm change, paradigm shift, paradigm driven, and paradigm expectation to describe experiments, which determine the way in which experiments are designed and interpreted. Kuhn saw a historical pattern in the way science develops over time. generations, even centuries, and by understanding the pattern, it is possible to predict how old paradigms are abandoned or morph into new paradigms. He shows how to identify when old paradigms are creaking and need to regenerate. The list below is a summary of 6 stages: normal science, puzzle solving, forming of paradigms, identifying anomalies that drive research, crisis, and revolution. Normal science is based on the acknowledgement of prior scientific achievements. Puzzle solving is explaining the observations of phenomena in terms of known science, which leads to better understanding. A paradigm is an accepted plan, a single group of theories to give a rational explanation to a phenomenon or puzzle. Anomalies are observations that cannot be explained within the framework of an accepted theory or paradigm. Crisis. All crises begin with confusion, the blurring of a paradigm, and need to loosen the rules of normal research. A revolution in science changes the common worldview, the ruling paradigm, and the way scientists think. Also, the related terms paradigm and paradigm shift widely used as from the mid-20th century onward, but some scholars do not see the term paradigm as adequately defined. Ian Hacking, in his introductory essay to Kuhn's book, describes the sense that Kuhn used the word paradigm. Hacking says paradigms, quote, can be read in endless ways and put to many uses. Kuhn himself admitted that he lost control of the word. Kuhn's view of paradigms has been criticized in detail by Margaret Masterman, who claimed there are 22 different applications of the word. In this book, the concept of paradigms will often substitute for a variety of familiar notions. A paradigm is a fundamental unit of scientific development, a unit that cannot be fully reduced to logically atomic components which might function in its stead. Kuhn cites Aristotle's analysis of motion, Ptolemy's computations of planetary positions, Antoine Lavoisier's application of the chemical balance, Maxwell's mathematization of the electromagnetic fields as paradigms. Exemplary instances of science are typically to be found in books and papers. Kuhn describes great texts as paradigms: heliocentricity, geocentricity, Ptolemy's Almagest. Such texts contain not only the key theories and laws, but also, and this is what makes them paradigms, the applications of those theories in the solution of important problems, along with the new experimental or mathematical techniques. According to Kuhn, paradigms are not a fixed, but a changing set of theories, but a dynamic system, a bubble of theories or ideas with a permeable, flexible skin, where the constituent theories are continually scrutinized, a shared constellation of beliefs, values, and techniques embraced by a particular community. Beliefs, ideas, and theories change with advancing knowledge, so the outer skin of developing theories must be flexible. Richard Tarnas says, there is an appreciation of the plasticity and constant change of reality and knowledge, stress on the priority of concrete experience over fixed abstract principles, and a conviction that no single a priori thought system should govern belief or investigation. Kuhn describes the term revolution, which is often associated with political revolution, where one political ideology overturns another, usually by force. New discoveries may also lead to a complete change or revolution, for example, in the style and standard of living and the way people think. But there are other kinds of revolutions: cultural, social, and scientific revolutions. Kuhn sees scientific revolutions as indicators of cultural change and belief. Scientific revolutions can change the way people think, including scientists. Some examples of scientific revolutions are Pythagorean philosophy, Hippocrates, the father of medicine, Aristotelian philosophy, Ptolemy's geocentrism, Nicholas Copernicus's heliocentrism, the Industrial Revolution, Pasteur's germ theory, the Communications Revolution, Morse code, Marconi's wireless communication, the Computer Revolution, and the list goes on. All of these brought cultural and social change, because cultural and scientific revolutions are interrelated, where logic and reason demand change. But there is a negative side to paradigm development. If paradigms lose their flexibility, they cannot incorporate change from the outside. Some examples of change by a scientist who thought outside the existing and accepted paradigm. In Britain, the idea of X-rays were originally thought to be a hoax. X-rays were discovered by accident. They were denied to exist by a leading scientist of the day, Lord Thomson, because it did not fit the box. When X-rays were to be seen as a form of light, and everything fell into place, Thomson was thinking in terms or rigid paradigms of his own experience, effectively saying, "I am a leading scientist of the day. How can I not know about this?" The discovery of wireless communication is another example. Marconi was only one of several scientists working with wireless communication at the turn of the 19th century, but he is a well-known name because he helped commercialize the practical use of wireless, receiving the Nobel Prize in 1909. But early on, he was ridiculed by mainstream scientists of the time for his ideas about wireless communication over long distances around the globe. Critics said the curve of the Earth would be a barrier that would deflect wireless waves by the equivalent of a wall of seawater 125 miles high. They were wrong. In 1903, Marconi launched a transmitter, at his own expense, on a huge kite in Cornwall, England, and transmitted a successful radio message in Morse code to Newfoundland. This was a revolution indeed, and a new communication paradigm was born that changed the world. Scientists are often wrong. Marconi's ideas certainly caused a rapid paradigm shift, and by 1906, nearly all ships of the British Navy were fitted with wireless communication, and today the mobile cell phones are ubiquitous. Out with the old, and in with the new. Louis Pasteur faced a mountain of criticism from his own colleagues against his germ theory. Fortunately, this made him more determined, producing more rigorous experimental procedures and plans, which demolished the miasma paradigm. Many thousands of lives were saved in the 19th century alone by doctors simply washing their hands between dealing with each patient. Glenn Seaborg, as a young chemist in 1944, suggested moving 5 elements in the periodic table to be with the lanthanides below the existing periodic table. His colleagues advised him, "Glenn, do not do this. You will ruin your scientific reputation." Seaborg decided he did not have a scientific reputation and went ahead receiving the Nobel Prize in 1951 for his contribution to chemistry. People who oppose grand narratives or ruling paradigms are often referred to as conspiracy theorists, a pejorative term often leading to ridicule and rejection. Historical figures such as Pythagoras, Hippocrates, Claudius Ptolemy, Copernicus, Kepler, Isaac Newton, and Pasteur were all at first conspiracy theorists, exposing anomalies, devising new theories, and eventually new and better paradigms. But when anomalies are observed in heliocentricity today, for example, they are more often than not dismissed, ignored, and ridiculed. One of the main problems with mainstream sciences, scientists become the sole arbiters and critics of their own paradigm beliefs and lose their flexibility, become concretized, making change impossible. Astronomy is a typical example of a monolithic, closed elite group ignoring any other cosmological models. Richard Tarnas comments, "To an extent never consciously recognized by scientists, the nature of scientific practice makes its governing paradigms self-validating. The paradigms act as a lens through which every observation is filled and is maintained as an authoritative bulwark by convention. Through teachers and texts, scientific pedagogy sustains the inherited paradigms and ratifies its credibility, tending to produce firmness of conviction and theoretical rigidity not unlike education in systematic neurology. Fixed on immovable ideas, paradigms become concretized, and this applies it to theological thinking. In theology, it is called dogma. For every observed fact presupposes an interpretive focus. In science, These conjectures must be continually and systematically tested. At any time, a new test could falsify it. One of the great difficulties of experimental research is how the results are interpreted. Tarnas continues, the problematic conclusion was reinforced by the newly critical approach to philosophy and the history of science, influenced above all by the work of Karl Popper and Thomas Kuhn, drawing on the insights of Hume and Kant. Popper noted that science can never produce knowledge that is certain or even probable. Man serves the universe as a stranger, making imaginative guesses about its structure and workings. According to Kuhn, a paradigm is said to be complete when there are no longer any questions to ask. He suggests that two paradigms in particular may be considered to be complete: the pendulum, eventually mathematically modeled by Isaac Newton, and Newton's optics, but this is open to debate. The danger is when people stop asking questions and concretization sets in. There are, however, stable paradigms such as Thomas Young's wave theory of light, and later wave-particle duality, and other fully quantitative paradigms such as thermodynamics, with theory of light and electromagnetic spectrum, all of which have produced laws of science, demonstrated by making very accurate predictions. Realistically speaking, it can be argued no paradigm is complete and must surrender itself to eventual adjustments and changes. Arguably, paradigms are never really complete because there is no foreseen end to knowledge. Paradigms are important, like stepping stones in pursuit of scientific truth, and must inevitably change in order for science to grow and move forward. Paradigms become necessary because eventually there is a need to define rules and laws in order to make predictions. Kuhn used the term normal science, which is used to investigate anomalies within paradigms when a paradigm ceases to function effectively. Without a paradigm, writing definitions, setting rules and laws, terminology and specialist language would be problematic. Kuhn discusses the defining characteristics of scientific research, seeing scientific revolution through paradigm change. One of the first attempts to record and classify the sciences was Aristotle. Aristotle was a polymath, a great intellectual of his day, a philosopher, mathematician. He wrote about politics, ethics, medicine, astronomy, physics, and life sciences. Aristotle expressed theories to explain phenomena as he saw it at the time, within the confines of knowledge that existed at the time. The majority of Aristotle's work, written in classical Greek, has been lost, and only about 1/3 has survived, thanks to Arab scholars. Arabic translations reached Western Europe about the 12th century and were translated into Latin, the common language of scholars. Scholars such as Roger Bacon and Thomas Aquinas helped introduce Aristotelian philosophy into schools and university curriculums across Europe. Aristotle's surviving works give insight into the ancient Greek mindset, but also to the 21st century mindset. Aristotle's theories and ideas may seem nonsense today, but not at the time. According to Kuhn, one of the reasons Aristotle's plethora of paradigms lasted for so long is simply because there was nothing better. And paradigms change when they fail to answer questions, and when something better comes along. But nothing better came forward until the 17th century, when traditional Aristotelian ideas were challenged. Aristotle was the only text in the philosophy of science in the West, and lasted for over 1600 years, but change was painfully slow. Galileo was an Aristotelian, but was one of the first to challenge Aristotle. For example, Aristotle saw the pendulum swinging as constrained falling, but Galileo, however, looked at the swinging body, saw a pendulum as a body that almost succeeded in repeating the same motion over and over again, ad infinitum. The better description, of course, came from Christian Huygens. Finally, Isaac Newton presented the solution as an elegant mathematical formula which enabled the behavior of the pendulum to be fully explained, mathematically modeled, and used to make accurate predictions. Taking Hippocrates as an example, Hippocrates saw the human system composed of 4 humors: black bile, yellow bile, phlegm, and blood. Humors were seen as chemical systems regulating human behavior, and disease was due to a deficiency in the four fluids being out of balance. Sounds like a mechanic describing the internal combustion engine, but at the time there was nothing else that even resembled what is now understood to be science, and it was all recorded and written down for posterity, and it all made sense. As Kuhn says, paradigms appear to be true at the time and make sense. The Aristotelian and Hippocratic paradigms endured for 1600 years and embraced by the greatest academic minds of the Middle Ages through to the Age of Reason and Enlightenment. Until something better came along, Hippocrates and Aristotle were the only recorded paradigms they had. But finding better paradigms to replace them was long and very slow. The formation of a new paradigm is often born of conflict. As new knowledge from experiment and observation arrives, more questions arise that cannot be answered by the existing paradigm, so the paradigm is often ignored, giving way to cognitive dissonance. After all, who would dare challenge the great Hippocrates, the father of medicine, and Aristotle, the godfather of evidence-based medicine, the fountain of wisdom and founder of many scientific paradigms? But both Hippocratean and Aristotelian paradigms fell with a great crash, as research revealed more knowledge and a deeper understanding of human biology, William Harvey's blood circulation, Edward Jenner's inoculation against smallpox, Louis Pasteur's germ theory, and so many other pioneers of medicine. The phlogiston paradigm asserted that all matter is made of four elements: earth, fire, air, and water. A rather crude, simple modern example of the phlogiston theory with a modern twist. Take a hair comb made of recyclable plastic and gently and progressively heat the comb. The comb is at first solid, earth. Heat the comb and it melts to a liquid, water. Continue to heat it and it becomes a gas, air, and eventually burns, fire. What was left was phlogiston ashes. The phrenology paradigm lasted only a few decades at most. Miasma is the theory that disease was caused by bad smells. This assertion is perhaps the most extravagant manifestation of a belief that prevailed in the medical profession for much of the 19th century and survived in some quarters into the 20th century. This belief held that most, if not all, disease was caused by inhaling air that was infected through exposure to corrupting matter. Such matter might be rotting corpses, the exhalations of other people already infected, sewage, or even rotting vegetation. The miasmatical explanation of the cause of disease figured prominently in the long debates among the people who were responsible for combating the cholera epidemics that afflicted Britain between 1831 and 1866. The downfall of the miasma paradigm started with a serious outbreak of typhoid fever in the 19th century London. A doctor noticed that the victims got water from the same water pump. He reasoned that the infection was from the water, and had nothing to do with bad smells, which was a result of poor sewage management. Other developments in Europe, such as Pasteur's germ theory, after further research and debate, the miasma paradigm was abandoned. At least two other medical paradigms fell for the same reasons, as a result of observation of anomalies, leading to research and new and better paradigms. The discovery of how to artificially produce insulin, the first of many hormones to be produced. Before artificial insulin, type 1 diabetes was a fatal disease, and most treatments were unsuccessful. But since the 1920s and until now, millions can enjoy an active and full life. A revolution in medicine based on normal research. The discovery of penicillin, based on simple observation in the 1920s, Alexander Fleming and Howard Florey, saved millions of lives of people, including World War II soldiers on the battlefields. Before penicillin, people could die from simple grazes and wounds by bacterial infection. This is another example of a revolution based on science research where old paradigms are swept away and replaced by new and better paradigms. The Pythagoreans were a Grecian cult who existed in Magna Graecia, a Greek colony on the toe of Italy. They believed that the whole world, including the many scientific phenomena, could be explained by rational numbers. A rational number is a real number and can be expressed as an integer, a whole number, or a fraction, for example, 1, 2, 3, -1, -2, -3, or 3/4, 1/2, 1/5, but the square root of 2 is irrational and cannot be expressed numerically. But the square root of 2 can be drawn, so it must exist, but as an irrational number. The Pythagoreans were absolutists, rigid and immovable, and this was the reason their paradigm crumbled. What did the Pythagoreans do when they recognized their fundamental beliefs were wrong? Did they say something like, "Sorry guys, we made a mistake, but never mind, let's take it on the chin and move on"? No, they made it a secret, and anyone who told the secret was murdered. Such is the power of secret societies. Hippias of Metapontum, a Pythagorean philosopher, was drowned at sea for breaking the Pythagorean rules in secrecy, showing that some numbers cannot be expressed as rational numbers, and thus exposing the falsity of Pythagorean dogma. Now this does not seem a big deal in this day and age, but it was at the time, because the Pythagoreans were rigid and concretized in their beliefs, embracing many absolutes, and were unable to compromise, an attitude that still exists today in modern astronomy. The irrational number was an anomaly, and anomalies are important and should never be ignored. The square root of 2 must exist because it can be drawn, but it cannot be expressed fully in rational numbers. Astronomers today, who do research only to confirm their beliefs rather than make new discoveries, make the same error as the Pythagoreans. They claim the mean distances of planets and the Sun from Earth are absolutes. They claim the mean distance of the Sun from Earth is 93 million miles, and make this value an absolute, called the astronomical unit, AU, in which all measurements to stars, planets, and distant galaxies are measured. But a closer study shows this distance is undetermined, and no more than a guess. Recall David Hume's example: all swans are white. But this is only true until a swan of a different color is found. Then the absolute fact crumbles. History shows that scientists should be very careful before declaring absolutes. Another example is Max Müller, who wrote a pamphlet challenging Charles Darwin on the evolution of human language. Darwin called Müller a dangerous man. Why was Müller dangerous? Because Müller claimed that language was sophisticated at the beginning and could not develop from grunts and groans of primitive man. This was seen as a threat to the new evolution paradigm. This claim is supported by Noam Chomsky, an American theoretical linguist born in 1928, who argued that a single chance mutation occurring in one individual in the order of 100,000 years ago, instantaneously installing the language faculty, a component of the mind-brain, in perfect or near-perfect form, was hard to accept or prove. Similarly, when heliocentrists today are confronted by alternative models presenting plausible evidence based on observation and simple experiments, they feel threatened and react accordingly, and often retaliate with ridicule. Beliefs deeply entrenched in the mind have become concretized and rigid dogma, and asking the wrong questions undermines deeply entrenched beliefs. Beliefs are often established in childhood by parents or teachers, and as they grow, it becomes unchallengeable truth. The old Jesuit saying, "Give me a boy until he is 7, and I will give you the man," may well be true, since the brain is soft and flexible in the early years, and early conditioning is hard to remove. So new ideas are always met with suspicion and healthy skepticism, and so it should be. When long-standing beliefs are challenged, they nearly always encounter resistance at a socio-cultural level. One of the problems of research is interpretation of the results. Experiments often conform to the beliefs and expectations of the experimenter, and data is valued through the existing paradigm lens. A good example is the phlogiston paradigm referred to earlier. The ancient Greeks believed that all matter was made from 4 elements: fire, earth, air, and water. An Aristotelian paradigm that was accepted for centuries by the finest minds of both the ancients and the medieval period, recast in the 17th century scientists. But it was the element of air that proved to be its undoing. Phlogiston was thought to be a substance without odor, mass, or color. When a substance burned to ash, a theoretical substance, phlogiston, was released. What are now known as elemental gases, in the 17th and 18th centuries, were known as types of air. In the 18th century, Joseph Priestley believed he had isolated phlogiston as a pure substance. Joseph Priestley and Henry Cavendish both made a discovery of something when experimenting with gases. They called them airs. So when Henry Cavendish discovered a combustible gas with no odor or color and was effectively weightless, he believed he had discovered the substance called phlogiston. Priestley discovered that when red mercury oxide was strongly heated, it yielded an air that was combustible. When French chemist Anton Lavoisier heard of Priestley's experiment, he was doubtful and repeated Priestley's experiment in reverse by heating elemental mercury and producing mercury oxide. In his experiment, contrary to the phlogiston paradigm, which suggested that when substances burned, substance was lost, but Lavoisier's reverse experiment showed something was gained, because the resultant product weighed more than the original mass of mercury, so something appears to have been added. This was the final blow to the phlogiston paradigm, which was gradually abandoned. Kuhn suggests Lavoisier's observation was a scientific revolution that contributed to another scientific revolution in the understanding of the structure of matter and the development of modern chemistry. It was the reaction of Priestley and Cavendish, both believers in phlogiston, to Lavoisier's experiment that is of great interest. They evaluated their experimental results in terms of the ruling paradigm, phlogiston, within the framework of a presupposed paradigm. Their experiments were no doubt paradigm-driven and carried out to conform an existing belief, assuming the belief was valid in the first instance. Lavoisier, on the other hand, used a scientific methodology that completely changed the understanding of the nature of matter, resulting in a new paradigm, the particulate theory of matter, the belief that matter is constructed from atoms and molecules. Phlogiston was swept away. Whether Cavendish continued to accept the phlogiston theory is doubtful, but Joseph Priestley showed no change and died still embracing the belief. This example shows how difficult it is to dislodge ruling paradigms that are so deeply entrenched in the human psyche. It also shows how the new ideas, theories, and paradigms are very difficult to establish, largely because of socio-cultural and peer pressures. Most college courses use inductive teaching, where the student learns from textbooks in order to pass examinations, and assumes the textbooks are correct. Deductive learning, on the other hand, is where the students conduct experiments and are allowed to draw their own conclusions on the basis of the results of their own experiments. The problem with inductive teaching is when new research contradicts the textbook becomes obsolete, and every textbook would have to be revised and reprinted. Kuhn comments that when a past paradigm is repudiated, the scientific community simultaneously renounces as a fit subject for professional scrutiny most of the books and articles in which that paradigm is embodied. Most students and their teachers rely heavily upon the textbook, and Kuhn notes, until the very last stages in the education of a scientist, textbooks are systematically substituted for the creative scientific literature that made them possible. This reinforces any indoctrination and conditioning the student may have been subjected to. How is it possible, according to Kuhn, to know whether a paradigm is creaking and needs to change? Kuhn's answer is simple. When there are too many anomalies. This leads to crisis, and crises lead to revolution, and in turn, revolution leads to paradigm change. Anomalies are important and drive research. Astronomers, however, ignore embarrassing questions, as shall be seen. Astronomers do no more research because they believe they have found the absolute truth, and consequently are unable to move forward and see new perspectives. They cannot repair the house that is falling down, because they cannot see, blinded by their own group pride, refusing to listen to the critics.